question, you have to check this little point. And it's a quick check, but one has to do it. I mean, it's a little. So we check if M even psi M is even morphism in the sense specified there, and when is odd, psi M is an odd morphism. I don't know, is it more convincing like this? That is. Okay, so let's look at the. So we have to check what happens to this. And, okay, so this is. So remember M. So M even or odd. So it's psi of M tensor AN. So this is, when we move it on, so this is -1 parity of A, parity of M, psi of A times M tensor N. We saw this at the beginning. And so when we take this, so psi is, see, psi is in here. So this doesn't, so psi is even. So it is, so this is -1 parity of A, parity of M, A psi M, M. So psi M does what it should do. No, I understand the limit doesn't prove because it's really a quick check, but still, one has to check the parity. That is, this is really and then has to check also this, the psi M resulting, it is of this type. Okay, so it's, we need all of this because now we want to define, but I want to finish today this madness. Okay, so I want to define the right. What is the dual of an A module? It is I erase. So this is M check. Are all the morphism from M to A parity preserving and the parity reversing? And you can check for vector spaces that it is really what it should be, because if you take a vector, super vector space, if you take so vector space is a special type of A module where A is K. So you're looking at all F from K and N to K. You see, if you chose only the parity preserving, then when you hit the odd elements, you cannot send to the field. You should send to 0. But you see, I'm trying to explain. So this consists of all the maps of EI from K and N to K, sending the vector, say, x1, xn, psi1. So these are numbers, okay? These are all, let's write different because things are indeterminate. Say U1, UN, U1, And then you have to avoid wasting. What I'm trying to say is that here, when you take this, if I take the element 0, 1, and I send it to 1, so the function em plus n sends the vector 0, 1, which is odd, to the element 1, which is even. So I'm saying that you need all the morphism, also the parity reversing ones. Otherwise you will lose this, which you need, because the dual of the vector space you expect to have the same dimension as your starting vector space.
Well, it won't even be an A module if you don't take all elements.
Yeah, you have a problem.
The result of taking the dual has to be an A module. So.
Yes, yes. I mean, there is several problems. Now, this is okay. I have a lecture today about matrices in my linear algebra class. So every time you write matrices, you have a problem.
So the A is always K10, never K01.
K01, oh here, yes, it's A, always this, yes. I mean, K01 is a different thing we don't want. But in our case, we take A for the general. Okay, now, we now want to write coordinates. And as you know very well in linear algebra would be so nice without coordinates, right? But we need to write coordinates. So let me open a small parenthesis about linear maps and coordinates. So we take a linear map and we want to write in coordinates this f. And you see I know you will not be happy. So it's enough that we specify on the basis elements. So EK is the usual thing, right? It is 0 and then there is 1 somewhere 0. And all the elements will be these, will be so the point is that we need a convention. Because you see, usually we express, what would we do? We would express, here we put the matrix and here we put the coordinate, right? But I want to do something different.
This is absolutely natural.
It is natural.
Must be on the right.
Must be on the right. Franco, I want to give a piece because they should be on the right. Exactly.
Because
they should be on the right because when you do the composition, it's much more natural.
Absolutely.
However, for people used like me to put it on the left since very young age, it is difficult to think to put them on the right.
Those, if you want to use the matrix characters, you have to think of vectors as columns and scalars as one-by-one matrices that must be on the right. Otherwise, it is
the
not
coordinates
right.
on the right.
Absolutely.
See, we have one in the audience that is very convinced this is the right way to go. But the other people are less convinced. The point is that in the usual setting, whether you put this here or here, it makes no difference, obviously, right? Here it makes difference. So, what happens, you see, this is f of ek. So, when we say we apply a g to this, you see it is very natural applying g because it will be applied to this. So if I do g composed to f ek, I'm trying to motivate why I put it on the right. To be honest, Franco, this is a conversion.
No, there's one point. If you want to use matrix calculus, the product must be defined.
In fact, I'm writing now the product,
If
yes.
you think that vectors are columns, then you can multiply a column on the right by a one matrix, and not on the left.
So this is
Not the
g.
right. So
Let me write.
it becomes very nice when you use this convention. Also
Okay.
the classical.
So this is summation. Sorry. So this is. So this is G applied to summation of Vj, Aj, You see at this point that it is very convenient that there is Vj here. Because if we had this in front, it would be a problem. Because then we would have to know what happens to this G parity reversible. So there will be, instead we apply it to this. Gj, so it will be some B. So what do we say? So the index is saying here, so it will be Lj, Ajk. And then I forgot, EL. This is the usual product, row and column product. It's not different. Okay. In fact, I have it different here. Franco help me. Did I do the thing wrong? So this should be the row index, right? Yes. No, it is working. So it was around here. Okay. Okay, now we come to the hard part. So it's okay. Now I want at least to finish this madness because. So remember that we have this identification, but we want to get another identification for. The lead writes it very generally. I want to write it only for special case. So let us take oh, sorry, I go to PQ. It doesn't matter. Okay, so okay. Yeah. Right, here is so I want to establish this identification. Which now is very annoying because it should be a consequence on that one, but it doesn't matter.
Maybe you can forget about that.
That one, yeah, we can do directly.
You can do it directly.
Yes, so
In a
it's,
sense, it's more.
let's do it directly. Okay, so let's do something which is not what we want first and then we do what we want. I explain later. So, again, this is the same problem. This is a vector space which has this as basis, and then we write the scalar here. Your friends are not happy?
No, I'm happy, but I'm saying that maybe this can be done also without coordinates. It will work.
I know it can be done without coordinates, but let's write coordinates for my own sake, because now I don't know what it is without. No, it can be done without, I know what it is, but let's do with coordinates because we need the coordinates in a moment. So where does this go? It goes to no, EK down, going to, so this EK goes to, right, no, Franco is right, we should do without coordinates, because it's really the right way to think of it. Sorry. So if you have to, so this, so we take some omega n, and this goes to m.
Sorry. Maybe
I have not written.
n tensor and what? Maybe it's more natural.
In fact, it is more natural what you say, but we do later. Really, stay with me, really, because there are two choices that are natural in two different situations, so we need to look at both. But we wait. But let me write like this. Okay, so it is, in fact, Franco is noticing that here we put a sign, right? This is your problem, right?
Yes.
Exactly, there is a sign coming. Instead, if we were doing this n times, there is no sign if we do the other way. Let's write it. Because we need both of these. So this is m going to n omega n, no sign. Okay, this is maybe we should right, we should give names to this, right? I give a name, I call this, say I call this psi, this map, and I call this style line, just to give name to these maps. I want to finally define what the trace is, because after so much effort, we need to say the trace. No, we should wait to define the trace. So let me write what these are in coordinates in the case of this APQ. So this is summation, and then we have, you see
However, we can define the trace in this context.
What norm the same? You can or you cannot?
You can.
I know, I'm coming in a moment.
Without coordinates.
Of course, you can define without coordinates, and but yes, shall we do the coordinates later? I wanted to first write the coordinates and then write the definition of the trace. I don't know, it's more a matter of preference. But I write coordinates, then we do the definition.
Just one point. There is a natural identification of dual tensor.
Yes, of course.
With morphisms. And
yes, we're going there.
If you put the things the other way around, I mean, in basic linear algebra, if you multiply a column and a row, you get a matrix. So vectors times dual vectors means endomorphisms. If you do the other way around, you can switch things and you will get trace.
Okay, so Franco feels the need to write immediately the formula without coordinates. We will do this, and then we go to the coordinates to see really what it looks like. Because, I don't know, for me without coordinates is very stressful. To understand it is really... So let's write the formula. So we need still two more definitions. So there is one which is very simple, which is the evaluation morphism from M check tensor M to A, which takes omega and M tensor M and does omega M, not very smart. And then we look at this delta going from A the other way around, M check M, which takes the element 1, and if you specify, delta, we call it F. So delta depending on F, where F is a map from M to itself. So delta F takes 1 and associate psi minus 1 F. So here, if we take n equal to m, any map f from n to m correspond bijectively to an element here. And finally, as Franco correctly said, there is a way to define trace immediately. Trace of f is the evaluation composed with this delta. Evaluation of delta f. So there are no coordinates in this definition. Now it is, to me, is not immediate that this is the trace. So, let me say something, that this definition holds in both cases, super and non super. So this will become the trace in the usual case, and will become, so let me say a word before we compute. So if F is associated to a matrix ABCD, the trace of F, it will be trace of A minus trace of D. Okay? This is what we will see. And there is a plus if we are in the usual category. What do you want to say, Frank? You want to say something? Now we verify this. We verify in a moment. What is that you wanted to say? This is not the definition you have in mind?
No,
This is it.
Definition, that is very neat.
Very neat. Yes, in fact, coordinates.
Definition, but the fact is that you have to think of F as a tensor of a functional and a vector. And then, with the functional and the vector, what you can do? Evaluate.
It's very...
Absolutely natural.
It took me a while to understand. So let's do the coordinates, because for me it's very convincing, the coordinate thing. So where is... so this EK is going to... See, the problem is that... okay, let me see the problem. So we have to so I want to write EI, and then to apply J to this EK, EJ, EK, and then multiply by AIJ, which is JI, sorry. I wrote it JI, right. The problem is that here, see, I switched EI with EJ, so I need to put minus 1. Sign parity of EI, parity of J. Now, how can I avoid this sign? Because it's very unpleasant. I can avoid this sign if I say, okay, there is a morphism of this switch imperative. So I can look at APQ times, as Franco is saying, I have to look at this identification, then I will avoid the sign. It's very relaxing this, because I have, what did I write here? I don't want to write. And then when I go to the other, I have no problem, because EK will go without any sign. We go to E, I, and then EJ, EK, AEJI. So there is no sign, right? This is the trick. Okay. Now let's see what happens when I do the evaluation. I have to remember that I did this trick, so I have to be careful to put things back, and the sign will come. So it's, okay, so when I do, so this is done. Right, so I want to so this is my F, because I want to keep track of where things come from. So this is on this is the difficult thing. So this is the F that goes like from here to here. So I have to do, so the trace of F is the evaluation of delta of F. Now what is delta of F? Delta of F is this, right? Is the, because I wrote it here, delta. Delta is psi minus 1 of F, so it's the tensor corresponding to this F. So I have this F here. What is the tensor corresponding? It is this one. So it is evaluation of summation EI, tensor EJ, AJI, but right. I want to claim something more. There is a sign, of course. No, just no. Give me a second. I have to find my formulas because
sorry,
it's just difficult. So this is F of E, because this is a delta, right? This is delta JK. So this is E F of EK. Right, this thing is F of EK. Right. No, I made a mistake here.
No, I think you're right.
The JK, no, so EI, AJI, is because what I want to make a claim, but
So you need
no, I need some time.
it works.
I know it works. I want to see this. Why do there is a sign? There is a sign now that is not right.
Sì, sì, non chiaro.
Funziona?
Perché deve scambiare che
No, you have to switch because evaluation.
No, I know.
Evaluation si
You
fa
have to have-
M2 times n.
No, but I want to claim.
So you have to switch.
No, there is a problem because there are two indices here I'm summing, right? And I want an index only. This is what annoys because.
Because
Yeah,
we have one dual.
Cross
Yeah,
term
do
to
it.
zero.
Huh?
The cross term
We have
to zero.
dual.
Right? So, okay, let's do as you say. I see a problem, but okay, maybe there is no problem. Okay, so let's go. Maybe it's working. I wrote a different here. It was working. So this is. Now we have to switch because evaluation. So we have to write. Okay. We have to switch these terms. So this crosses this and crosses this, right?
They are scalars, so the only crosses between.
No,
I
they're
and
not
J.
the scalars, Franco. These are elements in A, which has parity I plus J. So, but it may work anyway. So, you have to write, so this thing has parity. No, I think it's coming. I think it's coming because the parity of this object is parity of J times parity of I plus parity of J, right? This is the object. Yeah, you have to, before you switch, you have to know the parity of this, right? Me too, I have to go, but I don't want to be late at the other class.
So
But
you, I think you have to switch just EI and EJ. Why you need to switch also the coefficient?
okay, let's try to switch it. So it's -1, parity of I, parity of J.
Right.
EJ.
Cancel EI.
JI,
And then you know that the bases are dual of each other.
right? But
So
see, but this will destroy the sign, right? Because
no,
no,
you will have a -1 when I equals J is bigger than M, which is what you want. I think.
no way. Okay, so you do the evaluation. I'm confused because I follow a different procedure here, so I'm confused. So it's summation of -1, and then you do parity of I, parity of J, and then here you have so you have the summation of A, I, right? And then you do this.
Yes.
Ah, right, of course, yes, now it's come. I'm sorry. Yeah, I'm glad because we follow different procedure from the linear, but sign is still good. No, of course, yes. So when I is greater than M, no, but Frank was very nice, but if you interrupt the calculation like this, is very difficult. So it's, okay, so this is coming A11 plus A22 plus AM minus AM plus 1, M plus 1, minus AM plus N, M plus N. So it is really not different. That is the whole thing. It's very painful. It happens for the transpose too. But I will write the formula only. I'm glad that...
I mean, the only thing that is different from the classical case is that when you make that swap, there is no
I
sign.
know. But if you want to look in coordinates,
Right,
it's
yeah.
not so simple to see. That is the... Okay, so so check that the transpose of two maps, if you have the same map F and G, is -1 parity of F, parity of G, transpose of GF. with this new definition when you switch. You check this. And then you are ready to check that SLMN is really well defined, I mean, it's the correct object. I want to do a small remark on transpose. So when you do the transpose, you have that, so if you have a matrix M and you take M transpose, we know that in the classical setting, this operation is an involution. So if you do the transpose of transpose, but here no, is order 4. Transpose, transpose 4 times, because and if you have the transpose of A, B, C, D, the transpose is, so you do A transpose, C transpose, hopefully, minus B transpose and B transpose. So there is a minus sign appearing here. And the linear, of course, explains why the sign, it says it appears. But I'm sorry Franco is not here because Franco will give a very good explanation why it appears. But this is enough for madness on categories. And next time we go back to simple algebra, superalgebras, root and so on. So we go into the theory more. But I figure that one lecture should be devoted to this. I'm sorry. It's good to know that the strange condition on the trace, called the super trace, is not for fun, it's as a reason. As Franco was saying, we're making a mistake in linear algebra not to write everything on the right. Maybe today you should do it with the students. They're already so confused. Okay.